Good evening, everyone. Am I audible?
Yes, sir.
Okay, so this is right for now. Starters, I have shared my email ID and my YouTube channel link if you're interested in watching some previous videos. I had covered on electronics and special theory of relativity. For now, we are coming back to electronics. Last week we discussed electronics. This week and the next week will be on electronics. And before we begin, I needed to show and ask few things, so let's do that. uh, I hope you are able to view my screen. Can you see the screen?
Yes,
Okay, I'm not getting any responses. Are
yes,
you
it's visible.
okay? Okay, so so now my question is, as you can see, so the I usually take the sessions on Sunday evening. So I'll not be available. So the session 9 and session 10 have been rescheduled to February 1. This you must also have seen on the website, the Gate NPTEL website that they have, where they upload the topics that each of the mentor takes up. So there also it has been updated, and I request you to please take note. I'm sorry for rescheduling, but it was required. So this is the first thing. The second thing, and rather the more important one, is because if I remember, gate exam for physics falls on what when it will be 12th, is it 12th Feb? Am I correct?
11th, sir.
11th, that is Saturday. 11 would be
Yeah.
Wednesday, Thursday, Friday, Saturday. Yeah, 11th will be Saturday. Okay, so because I take sessions on on Sunday, so my 12th session will be, I mean, I don't know whether should I even take it or not, but so if I want to, what I am hoping was that I could combine 11th and 12th session again, let's say a 2 hour session. So my question to the people attending today is that would you want it to be doubts, or you want it to be a specific topic? By doubts, I mean, let's say you have a doubt from digital electronics related to JK flip flops. It can be a gate question or not, or I take some specific topic, let's say quantum well. So you have to tell me that. So I'll take this issue again in the middle of the meeting. So for now, can anyone so I'll do a polling kind of thing. So right now I have 7 people, sorry, 6 people. So people who are interested in specific doubts, just say just raise your hands. I'll count the number of hands raised. People who want me to do doubts on the final session, the 2 hour session. Okay, so I see no hands raised. Means all people are in favor of a specific topic. Is that the position? Okay, you have to respond because I cannot take an informed decision. And so Amit Roy favors doubts, and okay, all the other people apparently favor a specific topic.
Sir, I didn't. I meant the other one, specific topic.
Specific topic. Okay, ठीक है. Then I have to choose that specific topic. Okay, so
Okay.
yeah. So okay, I'll see which topic can I choose. Maybe I'll let's see. I have to see which questions are remaining, and then I'll obviously you'll be informed about the session if it's happening or not. And so yeah, that's that. And maybe even after. Okay, let's see now. So that's what's happening. The people who joined late. There's an announcement which you can see on your screens, hopefully, that the session 9th and 10th, which were on January 22 and 29 respectively, have been rescheduled to February 1, that is Wednesday, and the time slot is also correspondingly of 2 hours, 6 to 8 p.m. The 11th or 12th session will be a specific topic, which I'll choose and obviously inform you. So whatever happens, you will be updated. So now directly jumping into the slides. Again, my name is Amit. Welcome to Gate Physics live mentoring sessions hosted by NPTEL. This is week 8. Today is January 15, 2023. And this is again a second announcement which I had been talking about, I think, for a couple of weeks, or I think last week. Please join the mock test if you have not joined. Inform your friends and colleagues from other disciplines also. It's good to have mock tests, practice mock tests, because 3-hour mock test, you'll have that that training, that physical and mental training to sit in one place, especially in places where it's cold. It's a good practice to sit for 3 hours on a table and a chair doing with the online filling and online calculator, and it's good to practice. So please take avail of this opportunity, right? So I'm still hoping you can see my screen. Yes.
Yes, sir.
Okay.
Yes, sir.
Okay, so today's first question will be on Zener diodes. So this is the question. This is a fairly old question from 2011, 12 years back. So the question asks that we need to, in the following circuit, we need to find the current flowing through the 2 kilo ohm resistance. Now there are many information that is missing. Oh, first of all, the information that is present in this question is, you can see that, you can fairly see that these are symbol of resistance and they have a value of resistance associated with that. What we are normally habitual of not seeing, however, just hold on a second. What we are not habitual of seeing, however, is the fact that where is it? Yeah, this diode symbol is usually a triangle and a flat line, but this is a different symbol. This is the symbol, by the way, of a Zener diode. We'll be talking a bit about it. And a Zener diode also has some value written associated to it. Note that the voltage source has a value written next to it. This means this is providing 30 volts. However, the Zener diodes also have a voltage associated with them. We'll see what it means. So, but this is a good, so this is a symbol, and the good way of identifying is that there is a voltage written right next to the Zener diode. So we'll find the currents and the voltage through this resistance. This is also sometimes referred to the load resistance. Right, before we do that, let's quickly look into what a diode actually is. A very brief overview, nothing in deep. So these actually, if you have seen in your labs, this is what it looks like. So this is a physical diode which you can find in market. However, when trying to analyze a diode on paper or computer for that matter, we just need to model it. So diode is a complex device. It's not a straightforward device like a resistor. For instance, forget about temperature. So let's say you apply a voltage, let's say VA and VB, and there's some value called R. So current is very simply VB minus VA upon R. So it's a very straightforward expression between V and I. The relation is very straightforward. In diode, it's not so, because a diode, for a very simplistic model, you can on the center of your screen, so this is the symbol of a diode, by the way, a triangle followed by a straight line. So this is the symbol of a diode, and we can apply a bias here. So bias means a voltage source in this case. So let's say I'm applying an VD. Let's say this is the voltage you're seeing on the x-axis. So if VD is positive, this is said to be the forward bias regime. By the way, this is a PN junction. This triangle is an N. So P, and this is how a diode is formed. So this region is called the forward bias, and the region on the left half of your of this y-axis is the reverse bias. The plot is ID versus YD. This is the symbol, and we model this symbol as that in forward bias we say it's a switch. This means it's not dropping any voltage, it will conduct huge amounts of currents. In reverse bias, it's open circuit. You see there's a zero current here, and again no voltage is being dropped. So it's a very simplistic model. However, this is what I call a semi-real diode or a semi-ideal diode. In this case, however, the symbol remains the same, obviously, but in the forward bias, you have a finite drop of 0.7 volts. It's not 0 volts, so only after 0.7 volts this diode will start conducting. By the way, this is usually for silicon. 0.7 volts that I'm mentioning here, it's for silicon-based PN junction diodes. Right, while the reverse bias remains the same, reverse bias remains open circuit, so that part doesn't change much, but this is the important thing. So 0.7 volts is in semi-real or semi-ideal diode. More often than not, in your problems in GATE and other exams, this is the model that will be used. So you must be familiar with how to solve circuits using this model. That's for that's for your exam perspective. However, for an in-depth understanding which may be required in let's say when you go for interviews, you might need some more nuance, some more in-depth understanding. So this is, just forget about that this is Zener diode or not, just forget about that region for the time being. So what we saw in the last slide was that semi-ideal diode was behaving something like this. Right, this was 0.7 volts for silicon, by the way, 0.7 for silicon, while it's 0.3 for germanium, if I'm not wrong. Excuse me for a second. Yeah, Amit, go ahead.
So your screen looks stuck with one slide. Means it is showing only the diode modeling screen.
Even now, I am on Zener diode currently.
No, it. I was confused for a bit, but now I'm sure it's stuck.
Okay, let me then. Can others confirm? Can somebody else confirm which slide am I on?
Diode modeling slide.
Okay, okay, I'll
But still should.
okay, I'll stop presenting and then I'll rejoin. I'll rejoin. ठीक है. Sorry for the. Uh, just hold on a second. What can you see now?
Diode
And diodes.
And now?
Figure one. Yes,
Zener
Zener diode.
Okay. So was this complete diode modeling? Were you able to see the slide and my writing? Everything?
No,
only the
sir.
slide, no writing.
Okay, fine. Okay, fine. I'll just quickly revise. So on your in the middle of the screen is your ideal diode. So by the way, this is the symbol of a diode. These are the diodes that you can see in the market. So this is the symbol of a diode that you are seeing. What we do is that a diode is a fairly complex device. It's not simple like a resistor. So in a resistor, what you do is you provide two voltages and you can simply see I equal to V2 minus V1 upon some number which is usually the resistance R. So I and V relation is very straightforward in case of a resistor. It's not so simple in case of a diode. So you can see that it's so. For instance, if I draw I versus V of a resistor, it looks like a straight line. Sorry, it's passing through the center actually. I'll draw it again. So it's like this straight line I versus V. You can clearly see that this is not the case here. This is a very strange looking device. What it does is that, so it's an ideal case in the center of a screen, it's ideal case, which means that when it's forward bias, by the way, what do we mean by bias? So let's say we apply a potential to this, some battery to drive, and let's say this applied voltage is Vd. So this is the x-axis that you see. So if I apply a positive Vd, so it will behave like a switch, a closed switch, which you can see here, right? So it means it can conduct infinite amount of current, 10 volt, 100 volt, 10,000 volt, any amount of current, right? While the reverse bias, this means even for a voltage of let's say Vd equal to minus 0.1 volts, very small voltage, it will not allow any current to flow. Okay, that's called blocking a voltage. So this means so diode is a device which allows current only in one direction. Resistor can allow a current in both directions. Okay, so that's one of the major differences between these two. Okay, so next, however, as I told you, infinite amount of current is not possible. So this is a more what I we call a semi-real or a semi-ideal diode, in which we account that a diode will conduct any amount of current only after 0.7 volts. This is by the way for silicon. It's 0.3 volts for germanium. Okay, so that is a difference. Reverse bias remains the same. As soon as you apply any voltage below 0.7 volts, it will not conduct. It will show zero current. So basically in your problems, this is the most commonly used model, whether it's for gate exam or even for net or just exams. This is the most commonly used, although there are questions based on this model also, the completely ideal model, but most of the questions are related to this. However, if you are going for interviews and or for a more, let's say for a more in-depth understanding, you'll need to understand this diagram. We just saw in the last slide that it was something like this, I versus V, and this is actually a more realistic picture. So you can see it's not a vertical line, it's a slope, and here it's not flat. Again there is a slope to it, and in the reverse direction there is something called a huge amount of current is flowing. This is by the way called breakdown, that the diode has broken down. So here in this context, so this is what it looks like. The interesting thing, we are interested in a diode called the Zener diode. So Zener diode is exactly like a normal diode. This means it is a forward bias region and a reverse bias region. However, it has an interesting region called what happens beyond this. What is going to happen that beyond this regime? So what it does is that Zener diode always, if any current is flowing through Zener diode, it always says that I will drop only Vz. So this means that in the forward bias, by the way, it behaves like this. So we'll see in the problem, but let's say, so this is the symbol. Yeah, so this is the symbol maybe. Okay, so it's connect. There are some loads and some voltages and many circuit elements are there. So if it's forward bias, this means the current, so here the current will flow in this direction. You can see the polarity is high and low here, so current will flow in this direction. This means this Zener diode is biased in reverse mode, in this mode. So what we can say that we can replace it by simply a battery with VZ. We'll see, this will be more clear in the next slide when we solve the problem, but this is a more complete picture of a diode. And in specific, a Zener diode will always drop VZ, means it will always fix a voltage VZ across it, and this helps in regulating the voltage. Hence a question sometimes also comes, which of the diode can be used for as a voltage regulator. Writing it as a voltage regulator, because Zener diode always fixes in reverse bias a voltage VZ across it, hence it's a good voltage regulator. And we'll see in this problem which we are going to solve. So this was the problem, and we are required to find this current. This is the current that we are required to find. Since I don't have many how should I say, many tricks up my sleeve, what I do is that I solve it every question using KVL and KCL. So I'll do that. So I'll assume this to be the ground. So voltage here becomes 0, here becomes 0, and obviously here becomes 0 because this is a wire. So naturally the voltage here will become 30, right? And let's say voltage here I am assuming to be VD1, because this is the first diode that I am saying. Similarly, let's say the voltage here is VD2. Now you see I have labeled all the voltage or all the nodes with some voltages. Now let's also label the currents. So let's say current I is flowing here, which we require to find, and let's say current I1 is flowing through here. Excuse me. Yes, I don't know the answer yet. Let's see. And consequently, let's say current I2 is flowing here. Okay, so now what we are required to find only I, but what I have done is that I have broken down the problem. So let's say if the question asks what is the current I2, by this approach you can even find this. This will be a very simple approach because I know very few tricks. I can't remember formula apparently. All right. So now I know that. So now first we need to identify, as a step 1, we need to identify whether diodes are Zener or not. So we can see these are Zener diodes because of this symbol. So we'll say yes and yes. Why two yeses? Because there are two diodes. Second, what we need to find is that, is Zener reverse biased? So this is the question that we need to ask. Is this Zener diode reverse biased? So how you see it's reverse bias? So I told you this is the P terminal. This is the P terminal. This is the N terminal. If the voltage of N terminal is higher than P, this means it's reverse bias. So you see P is 0 here, and N would be, because the current will flow in this direction. So this value will always be greater than 0, right? Because you can see the current is flowing in this direction. So voltage VD2 will always be higher than 0. This means this diode is reverse biased. And if current is flowing in this direction, VD1 will be higher than VD2, right? This means which VD2 is also based on this, based on the current through I. If the direction indeed this, then I can write VD2 minus 0 equal to I times 2K. This will give me VD2 equal to I times 2K, which is greater than 0. This means D2 is, this is D2, this is D2, this is T1. This means D2 is reverse biased. So we identified that, right? Now let's see, let's write VD1 minus VD2. I'm writing Ohm's law across 1K. So this is Ohm's law across 1K. This should be equal to I1 times 1K. This will give me VD1 should be equal to VD2 plus I1K. Now VD2 is greater than 0. We saw that, and I1 is a positive quantity. So VD1 will also be positive. This means again the N terminal of this D1 diode is at a higher potential compared to the P terminal, which is at 0. This means D1 is also reverse biased. So these are the important things that before solving the problem with Zener diode, it's good that you get a picture in your, once you practice 20 questions, this will be clear to you, but for starters this is important, right? So what I'm going to do now that we have identified that all these, so this diode is reverse bias, this is reverse bias. Now we can simply say that VD2 equal to 10 volts because this is reverse biased, and we are assuming it to, now third is assume in breakdown. We'll assume it's in breakdown and solve the problem. Okay, so if it's in breakdown, this means the voltage drop across this resistor will be 10 volts. So I have assumed simply that whatever the rating is here, it's the voltage dropped across this diode. So VD2 will come out 10 volts. Similarly, VD2 will come out to be 20 volts because this is the drop across D1 diode. So VD1 I have, VD2 I simply had to find I. Okay, so I can simply say I equal to, so when I apply Ohm's law across this resistor by the way, so it will be VD2 minus 0, this is the ground that I had taken, V over R. R is 2K, so this will be 10 over 2K. This is going to be 5 milliamps. So we find the answer. And someone post in the comment, the correct answer is indeed 5 milliamperes, but this is the way to reach there. Okay, so let's just complete the question. 5 milliamperes was the current, so this cannot be the answer, and this cannot be the answer. Second thing was voltage across this resistance. So this resistance, we saw this VD2 was 10 volts because this is the rating that is here. So this is coming out to be option D. So option D is the correct answer here, right? But these are the steps that we have to follow. Now what I'll do, I'll pause here for a bit, and I'll ask you if you have any comments or questions regarding the Zener diode that we had discussed. In the meantime, I'll erase it. So if you have any doubts or comments, please speak. I'll be more than happy to repeat if any concept that you might need some more insights on.
Excuse me, sir.
Yeah.
Can you go to the slide that I versus V graph?
The ideal one or the real one?
The real one.
Okay, just hold on a second. Let me clear this up because I will need it again. Sorry for this. Yeah. Okay, yeah, we are here. Huh.
So the Zener diode,
Yeah.
like as a voltage regulator, acts in the leftmost region, right?
Correct. So it operates somewhere over here. Yes.
Okay. Means if the voltage supplied is more than the constant Zener voltage, then only it will act as a Zener regulator.
Huh. Correct. Actually,
Yes.
Actually, it's in this region. See below.
I'm not able to see where are you implying, like.
Okay, so you see the voltage VZ.
Yes.
So in this region, you see this gray line here, right?
Mm-hmm.
So in this region.
Zero
Sorry.
means 0 voltage to VZ or
0 to
minus.
VZ. Yes, 0 to VZ. So when the reverse bias, that means it's only dropping this much. That's the main point. Across the Zener diode, only this much voltage will be dropped. That because see, you can flow any amount of current. You see this region. Just hold on a second. Let me choose a different pen just to make it more clear. So you see this region in purple.
Yes.
Just carefully see this region. What's happening in this, the voltage will remain approximately VZ, correct?
Yes.
You can apply any amount of voltage. The current will keep on increasing, but the voltage across it will remain constant, correct? It will get fixed at VZ. This means you can flow 10 milliamperes, 100 milliamperes, okay? But the voltage across it will remain VZ. That's the main point. That's why it's called a regulator. Okay.
Yes.
So it's beyond. It's in this. The magic happens. See, if you are in this region, okay, the voltage will be. Let's say you are at this point. So here, let's say VZ was 10 volts. Let's say you are here at 2 volts. So here the voltage drop will be 2 volts and current will be whatever this value is. However, if you are here, let's say the voltage will be 10 volts and current may be 10 milliamperes, 100 milliamperes. It doesn't matter. The voltage will remain constant. So we are operating in this regime here.
Okay.
This is the reason.
Can't we use it in forward bias? Like
we can.
The voltage is constant, right?
Correct. So you're saying so what you are going to do, you can only draw 0.7 volts if it's silicon, not more than that. So we do use that. That. So I'm forgetting a question. I think last 3 or 4 months back we solved a question which was something like this. 3 or 4 diodes were in series. Okay. And
Okay.
I think there was a something like this, and this voltage was, let's say, I think 5.1 volts or something. I forget the actual problem, and we are required to find the current through this resistor. And this value was given, I think 1k or something. So you can simply find what's the voltage here. So there'll 0.7 drop here, 0.7 drop here, 0.7 drop here. So this will be 3 volts here. So 3 upon 1k is 3 milliamps.
Okay, so the same logic can be applied in forward bias, right?
Yes. Which logic are you talking about? You should be
Like
clear.
like it works in the
Huh. Yes. So by logic, am I audible? Hello?
yes, yes, sir.
Yeah. So by logic, I mean that it can support any amount of current, but voltage will not change. Yes. That is the logic.
Okay, and like won't it there be a short circuit if a large amount of current flows through it?
No,
Like,
so that's a good, that's a real problem that we encounter. So theoretically, you can see that I will flow 100 amps of current. Let's say.
yes.
I'll, that's not possible, because when a huge amount of current flows, there are many other non-idealities which come in. First of all, the temperature will be so large, and there are many things which happen. So every device has a power rating associated with that. So this is the voltage rating. This is 10 volts. Okay. This diode will also have a power rating, which will be in watts. Maybe like 50 milliwatts, 100 milliwatts, whatever. So even though you can drive 10 volts of current, okay. So if you say 50 milliwatts upon 10 volts, so that will be 5 milliamps. This means you can drive a maximum 5 milliamps through this Zener diode in reverse bias condition. Is it clear?
Okay. So it also acts like a resistance resistor at the same time, right?
You cannot say that, because see, for a resistor, you, as I told you in the previous, I think, yeah, so resistor has this typical behavior. You cannot say it behaves like a resistor for all the current and voltages, so that will be a misleading statement. It does drop power, it consumes power, yes. Resistor also consumes power. Resistor has a voltage drop associated with that, diode has a voltage drop associated with that, but I mean, they're not the same or even similar for that matter. So I should be very clear about it, so that there's no
Okay.
confusion. Yeah.
Okay, got it, sir. Thanks.
Okay. Yeah. Any other questions regarding the problem that we solved or the concept itself? Because Zener diode, it's very simple to understand. You just need to just make sure what the VZ is, and that's it. The problem becomes straightforward. It's just a voltage source then. So what we can do, I will redraw this circuit as something like this. 30 volts, this, 20 volts, 10 volts, and 2k. This is the circuit. This is 500 ohms, this is 1k. So let's say the problem asks you find this current, then it's very simple. You see the voltage here is 20, so current through this resistor would be 30 minus 20 upon 5 milliamps. So that will be, I think, sorry, 500 ohms, sorry, my bad. So you can calculate it. This will be maybe 20 milliamps, I think. Yeah. So by this approach, you can solve any amount of, I mean, you can play around, and whatever current you may want to find, you can find it, because we have already identified the voltage. If you know all the node voltages, finding current is very easy. You just use Ohm's law, right? So the people, I don't know how many of you were able to see this announcement. So there's a change in schedule for 9th and 10th session, which was to be on 22nd and 29 Jan, is now on February 1st, and time slot is 6 to 8. Please remember, it's 6 to 8. Usually we start at 7, but it's 6 to 8. And for 11th and 12th session, I'll identify some topic and we'll discuss that. Right. So before I move forward, any other comments on Zener diode? Otherwise, we'll jump into the operational amplifiers, which I believe is something you should know. Yeah.
So if we notice in that graph, so the graph was not passing through the, means it is cutting the x-axis in the positive x.
Oh, that's a mistake actually. It is actually, so it does pass through. So what happens is that, so this is something like this. So it is passing through this. So that was a,
Okay.
it is passing through that.
Okay, sir.
Yeah. All right. So now let's talk a bit about the operational amplifier. So it's made up of two words, as you can clearly see. Operational amplifiers. What do we mean by operation? Some of the very simple operations in mathematics are comparison, like x is greater than y, yes or no. Integration, differentiation, and addition, subtraction. So these are very basic operations that we encounter, not just in real life, but even the calculators that we have. So first of the primitive calculators did used to have addition, and so how to do that using op amps. Right, amplifier. In this case, by an amplifier we mean anything that implies the input voltage. So if you are applying, let's say this is a black box, you apply 1 millivolts. You apply 1 millivolts as input, and let's say you get 1 volts at output. Very good. It amplifies by a factor of 10 to the power 3. Obviously this is not coming at from random. There is some DC power supply to this. Let's say minus 5 volts here, plus 5 volts here. So that is there. So but it is amplifying the signal. Right. It's important to see that this is subclass of differential amplifier. So what is a differential amplifier? This is a differential amplifier. So what it does is that differential amplifier, the keyword here is difference. So these are the two BJTs, and what it does is that these two BJTs are fed two different inputs, V in plus and V in minus. So what we call this term AD is the differential gain. Differential gain means whatever is the difference between the two outputs, it will be multiplied by a factor AD, and that will be the V out. Also, this is called the common mode gain. Common mode. So whatever is the average of these two inputs, it will amplify by a factor of AC, and it will also be added to V out. Why did I call it a subclass? I called it a subclass. If you make AD greater than, if you design this circuit in such a manner that AD is greater than AC, and the output impedance is low, input impedance is high, what you will get is a differential amplifier, and this is the symbol of a differential. What you get is an operational amplifier. This is the symbol of an operational amplifier. So this V plus that you see is this V in plus. These are the same. This V minus is then V in minus. This Vs plus you see is this VCC. Vs minus you see is VEE. Okay, so and V out that you see, you can see over here is this signal, the V out 2 minus V out 1. So this is a modification of that, provided we designed it in such a manner. This means we choose the value of RC1, RC2, RE, and the parameters of these BJTs in such a manner that AD is greater than IC. We'll not go into how to achieve this. I just wanted to emphasize this. This is important. This is how this is how operation amplifier is an application of BJT or FET in that case. Right. So first we'll talk about what is an addition. So this is the circuit for this is a general circuit for an schematic of a operational amplifier. What is an ideal operational amplifier? So there are some terms which you call open loop gain. So gain means, you can simply say gain would be V out over V in. V out over V in would be your gain. So this is V out. V in would be this. This is V in. Okay. Ideally it's infinite, but it's ideal. So good operational amplifiers have 10 to the power 5 gain. What is the output voltage? So output voltage ideally denoted by V out can be infinite, which is not true. In this case it will be limited to whatever this value is, Vs plus. This is also called the saturation voltage plus. This is saturation voltage minus. Input impedance we talked about, like this input impedance. How much input impedance is on the input side. That's what input impedance. Ideally it's infinite. Real value is very large, maybe in mega ohms or something. Output impedance you see over this here. Output impedance is 0 ideally, but in real value it can be ohms, or if it's very good it's in milliohms or even smaller. We'll not go into the offset voltage or bandwidth or slew rate. This I can identify, this I can see. I told you, right, AD greater than AC. How to quantify this? So 20 log AD over AC is CMRR, common mode rejection ratio. Higher the CMRR, better the differential amplifier, because it's neglecting, see, it's neglecting this second term. It's taking into one only the first term, which is like V out equal to AD times V in. V in is the difference. So that's why this is important. So what we do is that, and this is again, if we take into account all the idealities, this is how your now operational amplifier will look like. So V out remains the same. Vins, both the Vins remain the same, and this is the Vsat. So plus Vsat and minus Vsat, and the gain here is denoted by this symbol A. OL stands for open loop. Why it's called inverting, non-inverting, we'll see in a minute. But this is the complete, this is how an op-amp will look like, symbol of an op-amp. Right, so what I'll do is that we'll just quickly look into what is a comparator circuit is. So comparison is fairly simple. This on the top of your screen you can see, if input voltage, this value, is greater than some reference voltage, then output should be high. If input voltage is less than reference voltage, output should be low. Very simple. If you are greater than some given number, the output should be high. If the input is lower than some given number, the value should be low. This is what is being depicted here. How it does that, it's we are not going to talk about it, but it does that. It's able to perform that function. This function is called the comparator function, or this circuit is called the comparator circuit. We solved last time a few questions on this, so if you are interested you can go through that. Right, this is a fairly, you can see now what we do, we add feedbacks. Why we need feedbacks is because you can clearly see that there are only two values possible in this case, VCC and minus VCC. Any value here is highly unstable. A very small, like let's say 1 millivolt of shift in input voltage can swing from the negative output to the positive output. We don't want that because there's always some noise associated with the input signal. So what we devise some feedback loops. So negative feedback is a stable output. Why it's called negative, it's because this is the output terminal, this is the negative terminal, right? This is also called the inverting terminal. Why inverting? We saw in the last slide, I told you. So this is why it's called inverting, because if the input is applied to this terminal, the output will be inverted. So output and input are out of phase. Out of phase means negative sign or 180 degree shift. So these are all the three synonyms: out of phase, negative times, or 180 degree shift. This is what happens if the output is connected to the inverting terminal. However, if the output is connected to non-inverting terminal, you see this positive, it's a positive feedback. Although this also gives unstable output, but it's good for oscillators. And one of the examples is the Schmidt trigger. So again, you can see that in your textbooks or some other videos. Right, now I'll get back to our problem because we are running a bit low on time. So what I'll do is that, so this is the problem that we have. This is a circuit that is given to us, and we need to find, we are given V inputs, and we are required to find the output waveform, how it will look like. So before we solve, we just check whether the question says something about the ideality of op-amp. So the question is silent. If the question is silent, assume it to be ideal. This is important. In some questions, it is specifically said it's non-ideal. Hence, you cannot ignore R in, R out, or other stuff. So you have to take into account in that case. But here, we can ignore all this. R in should be taken to be infinity. R out should be taken to be 0. Next, we find if there is a feedback or not. How to identify that? Go to the output node and see if you can go on some input node or not. So if I am here, I can talk to the input node. This is the non-inverting terminal, the plus. So I can talk, output can talk to the non-inverting terminal. This means, so there is a feedback present. What is the feedback? This is called the positive feedback, because output terminal is connected by some means, by some electronic means, to the positive terminal or the non-inverting terminal. Hence, there is a feedback, is the positive feedback. This is an interesting point, but this is a virtual short. So what I'll do is that I'll draw that Rn here. Okay, and let's say the voltage here is V plus, voltage here is V minus. So if I write Ohm's law across this Rn, like Ohm's law across Rn, so it will be V plus minus V minus, V equal to the voltage difference equal to, and let's say some current I is flowing through this, I times Rn, right? So I will come out to be V plus minus V minus over Rn, and we know Rn tends to infinity, right? So I will go to 0. This means V plus will approximately equal to V minus. What's happening is that if two voltages are the same, we call them a short. This means a short circuit. So what's happening is, even though they are different wires, right, they are not talking to each other. However, they are the same potential, and we denote this by we denote this virtual short by a dashed line. Dash means it's not physical, but they are shorted, hence we are connecting them with a wire. This is the virtual short. This is a very important property of an ideal op-amp. Okay, now we'll try to solve this problem. Let's now draw some voltages and currents. So since this is a virtual short, I am drawing this here. So this voltage would be whatever the input voltage is, which is V in. This voltage is V out, I know that. So what I'll do, I'll apply KCL on this node. So note that this is an ideal diode, so current here would be 0. I write I equal to 0. Current here would be 0 again. So both these currents would be 0. So if I write KCL here, and let's say I1 current is flowing here and I2 is flowing here. So if I write KCL on this node, let's call this node A. KCL at node A, it would be I1, the incoming current, equal to outgoing current, which is small I. This one, let's call this I1, and I2, I1 plus capital I2. Now I1 is 0, so I get I1 equal to I2. Right? How to get I1 now? If I apply Ohm's law across this 1 kilo ohm resistor, it will be 0 minus the voltage is V in. Note 0 minus V in upon 1K is equal to Ohm's law across this resistor, that will be V in minus V out over 4K. This is the resistance. K and K gets cancelled. What I get is 4V in, minus 4V in equal to V in minus V out. This will give me V out equal to 5 times V in. So notice that the output voltage is in the same phase as if the input voltage is positive, output voltage will be positive. So that's important. So what we mean is that now we can simply draw the diagram. How do we do that? So we know input voltage will always be 5 times, output voltage will be 5 times the input voltage. Okay, so let's say I start from this point, which is minus 5. Very good. So when the input voltage is minus 5, output voltage should come out to be minus 25. So we should say it's minus, but we cannot go beyond this. So if the output voltage somehow mathematically comes out to be greater than minus 25, it cannot go beyond minus 10. So it will remain minus 10. Right? It will increase above minus 10. So let's say when the input voltage is minus 2, again the V out will remain minus 10. So it will remain minus 10 up till this point. However, when let's say voltage is minus 1, when the voltage is let's say minus 1, what will happen then? When the voltage is minus 1, the output voltage would be minus 5 because it's 5 times V in. So it will be somewhere here. And when the input voltage is 0, the output voltage should come out to be 0. This means it should come somewhere over here. Similarly, if the input voltage is 1 volts, which is here, the output voltage should come out to be 5 volts, which is let's say here, and at 2 volts, which is this line, the output voltage should come out to be 10. So it will go something like this. If the input voltage is above 2 volts, let's say 2.5 volts, so output will be 5 times 2.5, which is 12.5, but we cannot go above 10. This is the limit. So it will remain stuck here. Okay, it will remain stuck until it reaches this point again. This point again, 2 volts. And then it will start its downward journey, and then like this, and then like this, and then like this. It will continue on its journey like this. I told you positive feed. This is a positive feedback circuit. I told you it behaves like an oscillator. You can clearly see it's oscillating over here. Right, so this is the waveform that we got. Let's see which of the output waveforms does it match. So we got something like this. Right, so does it match anything? So when it's negative, first of all, it has to be in phase. So when it's negative, it should be negative. So this cannot be the answer. Again, this cannot be the answer. Okay, let's say at 0. Right, I don't think there is any correct answer for this problem because this is the waveform that we have gotten, and I'm not getting any such output in the answer over here. So I mean, you guys have any comments on this? If I did something wrong, just correct me. I know I'm supposed to tell you, but it's a two-way street. I may have made some mistake. Is it correct though? Am I audible?
Yes, sir.
Yeah. Pratik, hey, nice to have you back, man. Again. Okay.
Yes, ma'am.
So yeah, so I'm fairly confident in. I mean, if I'm wrong, then I don't know. I don't think. Let me just.
I think it's good.
Sorry. The answer key says the answer should be A. I don't know how. I don't know how it will be A because this is completely out of phase with that.
Sir, but
You're not.
V in is
Sorry.
V in.
Uh-huh.
Hello, sir.
Yeah.
Sir, but you said that when the V in is applied to the inverting mode,
Uh-huh.
then the V output will be negative, means out of phase.
Sorry. I was wrong in that. When the I should have said when the. So okay, I should go back. You're correct. I made a mistake. So usually when the feedback is like this, input is applied here. Usually, okay, I am saying usually because sometimes the input is applied here also. So that's so the so you should not. I should have been careful. Yes, you are correct. It's out of phase only when the feedback is negative and the input signal is applied to the positive terminal. Then it's out of phase completely 180 degrees. Otherwise, it's not necessarily out of phase. And there are no capacitors also. So there are many conditions in that. I was giving a very simplistic picture that if the input is applied on this node and you're taking output here with connected with a negative feedback loop. So that's what I meant. In this question, what we did, the input was applied to the negative terminal and the feedback was positive. So we saw that they were in phase. It's 5 times VNL. You can see this over here. So that's what I meant. Yeah, I'm sorry for the confusion.
Okay, sir.
Yeah. Okay. I don't know how to. I mean, how to proceed now because I think it's okay. One thing I can be sure that they'll be switching at -2 and +2 or not. So they should switch here. But that also depends on the rising and falling also. So yeah, I mean I'll not comment any further. So that's that. So if you have any comments regarding the at least the concept part, I can take care of that. But I think the answer is wrong for this. So that's that. All right. Sorry for this again. Yeah, please join mock test if you have not. Now what I'll do, I'll combine the two things that we had talked about today, the Zener diode and the op amps. So let's see what happens. All right, I'll pause here again and ask if you have any doubts or comments. Please speak about the op amp. All right. Yeah, go ahead.
सर
हाँ
एक्सक्यूज मी सर
yeah.
सर मुझे स्पेशल थ्योरी ऑफ रिलेटिविटी से डाउट है
Harish, this is I'll try to stay back after this class. If other people
Okay,
don't
sir.
have any doubts, then we can talk about STR. And secondly, for others, if you have somebody else was speaking, yeah, please go ahead. I heard two voices, if I'm not wrong. Did also somebody else also have to say something? No. Okay, fine. So second thing what I wanted to say was, sorry. Yeah, if you have doubts, if you find that I am not able to take them in the session, please email me. That's why I shared my email address. At least 3 or 4 people have emailed me and I've tried to address their doubts to the extent possible. Because sometimes it's not possible to give the individual attention, although the people are here in these classes fairly low, but still. So if you find and from some other topics also, maybe just question or net questions, feel free. All right, so we'll jump into this. Question asked, which of the following circuits negative feedback does not operate for a negative input? So all the 4 circuits, 3 are fine, so to speak. One of them is not. One of them will not operate. That's what the term uses, operate. And the saturation voltage, by the way, these are this is a saturation supply, so VSAT. Remember, there's some VSAT over here, plus VSAT, minus VSAT. So this is talking about that. Okay, so it cannot go over plus minus 15 volts. We need to identify which one operates, which one does not. So let's go ahead. Again, ideal op amp, we'll assume all the op amps are ideal. Nature of feedback, question itself says negative feedback, and we can see output is talking to negative terminal in all the 4 cases. So all the 4 circuits are negative feedback. Virtual short, as I had explained earlier, so these will be at the same potential than inverting and non-inverting terminals, and we denote it by a dotted line. Right, so let's take the first problem. I'll invoke the virtual short here. Okay, so this means this potential will also be 0, and yeah, so let's say this is V in and this is V out, and let's say this is R1 and R2. I'll apply KVL along this route, or you can say the current flowing here should be equal to here because no current flows in. So I can simply say V in minus 0 upon R1 is equal to 0 minus V out upon R2. Sorry, this is R2. So if we calculate, we can find out V out equal to minus R2 upon R1 times V in. So see this negative sign? That's what I meant. If the so if this is grounded, or if the input is, there are many cases in which this can be negative, in which this is not negative. So I should be, so please see to that this is the typical configuration that we have. In this case, if the positive terminal is grounded and the input is applied here, you get a negative sign. This is out of phase. So as you can clearly see, this circuit will operate for every voltage of V in. You apply obviously it will saturate at plus and minus Vsat, but let's say V in is minus 1 volts, plus 1 volts, it will operate it will saturate obviously. So let's say if the V in is something like this, V out will be out of phase, but it will operate, and it may saturate also. So it may be like this, something like this, but it will operate for sure. So this circuit looks fine. Let's talk about this circuit now. So again, I am applying V in over here and V out over here. Now there is a diode, and that too a Zener diode. So what I'll do, I'll assume this is, so I'll take 2 cases when V in is positive. So, and let's just start to so again, due to virtual short, this will be grounded. So current will flow in this direction because this voltage is higher for case 1. Current will flow, so current will flow in this direction also. So this means Zener diode will be simply forward biased, right? And so current can flow in this direction. So this is a circuit, I think logarithmic or anti-logarithmic circuit. I'm forgetting which one, but it will operate because this diode can conduct. Remember, this is a diode and it can conduct, and it will conduct. What about second case, when V in is less than 0? So when V in is less than 0, what I'll do is I'll erase the ink that I have here, right? If V in is less than 0, so current will flow in this direction, because this resistor, this is a higher potential. So if then there is no current coming in or out of this op amp, so the current has to flow in this direction here also. Is this possible? Yes, this is possible. We remember this, if the voltage exceeds 5.1 volts, huge amounts of current can flow through this Zener diode, provided this V out is greater than 5.1 volts. Then the huge amount of current, so this circuit will work, will operate, but star, remember the terms and conditions. So the star says that conditionally, what is the condition? That this output, that V in should be such that V out exceeds 5.1 volts, and there are some other conditions. The resistance value should be low enough. There are many other conditions, but it can operate. The whole point is that it can operate. So the question asks which does not operate. So there is a condition in which it can operate safely. So B is also I think we are also safe as far as B is concerned, right? Again, now let's go to, this is V in, this is V out. Again, we will take case 1 where V in is greater than 0. So this is the same as previously. So if V in is greater than 0, the current will flow in this direction, in the right direction. So I'll draw it here itself. And this is a diode, so current can flow here also. So it will operate. There's no problem in that. Case 2 is interesting, when V in is less than 0. Now V in is less than 0. Now what's going to happen? First of all, I'll erase the ink that I have. Yeah, if V in is less than 0, this means this resistor will flow in current in this direction. So remember, this is again virtual short, this is 0 volts. Okay, so now in order to satisfy KCL, the current has to flow in this direction. And if the resistance is not very high, mega ohms or something, a diode will not support that kind of current, right? Because remember, the reverse bias of diode looks something like this, right? If it supports this much amount of current, it will break down. The diode itself will burn in this condition. And over here, it's very low current. It can operate, but it has again conditions associated with that, and conditions are much more severe. At R has to be very high, and voltages have to be very low, then only this will operate. So this is operating with a star. So operate but with a star, and this star, it has not one star but it has 2 or 3 stars, because the condition is much more severe here. Now let's come to this case, V in and V out. So again, case 1, V in greater than 0. This is case 1. What will happen is that, so the current will flow in this direction because this is virtual short. So this diode will function, D1 will function, right? So D1 will operate. D2 won't, because D2 will be reverse biased, right? Because this voltage will be higher. Current is flowing in this direction, right? So this voltage is low, this voltage is high. This D2 will be reverse biased. However, case 2, when V in is less than 0, D2 will operate. I'll tell you how D2 will operate. I'll draw using a different pen. So in that case, current will be like this. So it will flow through D2. Current will flow through D2 in this direction. D2 will operate, D1 won't. So this operating in both the scenarios. So if we see that this was fine, this was fine, this and this had some problems, but this has much more severe problems because it cannot conduct in reverse direction. Cannot in reverse. This can. Right? So the most appropriate option, right? Most appropriate would be C. So that's what my understanding is. This was a nice question. This was actually not a numerical that you typically encounter. Right? These days, such questions are not, very rarely asked. This is a question of 13 years before. These days, such questions are not asked. So this is more numerical type of, but this is the problem which can be asked in interviews very easily. So it's not like that, because after clearing the exam, you have to also think about the whatever you want to pursue in a job in a PSU or PhD or MTech or let's say opportunities abroad. Interviews are a core process, and there they test on not much on your correct answer, but how do you get to that answer. That's why such thing can help. Okay, so what I should do is that excuse me. So this worked fine, this worked fine, this we didn't know, and this had many questions, right? So what we can clearly see, between B and C, the more correct option would be C. So this does not operate for a negative input. So yeah, that's that. Oh, it's asking for a negative input. So negative input, this will be reverse biased. So this was V in, right? So this is reverse biased, this will not operate. So that's it. But we discussed positive input as well as negative in both the cases. So that covers all your bases. So that's it for today. I think, yeah, we are on time. That's very good. Just for the final time, I'm repeating it again because I don't want you to waste 2 of your weeks. The GATE exam is barely a month away. So and if you have doubts, I request please send. I'll try to take them up. So that's it from me today. Obviously I'll stay back for some more time. If you have any doubts in the problems that we discussed today, please speak. You want me to repeat something or anything like that, I'll be more than happy to help. Yes, I can share my email. Just hold on a second. So my email ID is learnwithamitbansal@gmail.com. I've just shared in the chat box, and also I've given a link to the YouTube channel I have. On this YouTube channel, I upload all the sessions that we have had till date. So usually I try to upload for instance, every Sunday there is an upload because there's a session every Sunday. So I request you to, if you are interested, that is, you can please go through some of the previous sessions. I had covered electronics topics, special theory of relativity. Yeah, electronics I have complete. I think I've completed every question from 2014 to 2022. Yes, every question of gate physics you can find there. So yeah, that's that. These questions today we discussed are slightly older. You saw 2010, 2011, because I had run out of questions. And that's why and if you are interested, you can also go through special theory of relativity and the topics: velocity transformation, Lorentz transformation, time dilation, relativistic energy, and stuff like that. So yeah, any doubts or comments about today's topics that we discussed?
I have a doubt related to decibel, that how we quantify things in decibel. For example,
Okay.
AD by AC, same number we have written in decibel. We also write intensity also sometimes
Okay.
in decibel.
So
Sometimes
okay,
it
so I'll yeah,
is confusing.
that's a very good question actually. So let just hold on a second. Let me find some slide in which we can talk about it. Uh, okay, I have to do this. Insert new slide blank. Is the screen visible? I'm not sure if it is. Are you able to see the screen?
Yes.
Okay.
Yes.
So decibel. So basically decibel is another way of okay. Let me ask you a question. Um, how should I put this? Okay. Uh, what is um, okay? If I ask you the distance between Sun and Earth, what units will you choose?
It is 150 million kilometer
So
approx.
150 and if million, if I'm not wrong, is 3, 4, 5, 6 kilometer, right? Correct?
Yes.
Okay, now let's ask you second question. What is the distance between your college, wherever you study or studied, to your hostel or home? If you're staying in a hostel, what is the distance between your hostel and your college for that matter, or your room for that to hostel approximately?
5 to 10 kilometer.
Okay, so I'll say room to college is 5 to 10 kilometers. Very good. What is a typical interatomic spacing? The spacing between two atoms in a crystal,
In
let's say.
angstrom.
Huh?
Angstrom. 10 to power minus 10 meter.
Yeah. 10 to the power minus 10 meter. Let's convert everything in meters, okay? SI units. So this is 6, 9, 12. So this will approximately 10 to the power 12, okay? This will approximately be 10 to the power 3, let's say. This is 10 to the power minus 10. I want you to create a scale in which you can express all three. If you draw in a linear scale, what you will see, lattice constant will be here. Your room and college will also be here. And distance between sun and earth will be somewhere here. So you not see points. What we do is we do a log scale. If we take a log of these three numbers, so this will come out to be 12, this will come out to be 3, this will come out to log to the base 10. Forget about the e or for time. This humans can easily say, okay, I know minus 10 is minus 1 minus 2. We are habitual of seeing this from like 6th or 7th standard. 1 2 3 4 5 12 will be here, 3 will be here. So you'll simply say, well, sun and earth is here, my room college is here, and lattice constant is here. You can visualize them in the same plane. Sometimes what you want to do, you want to arrive at nice numbers. Okay, you put multiply with a 20, you put the quantity whatever you want here, and this is what is called dB conversion. dB stands for decibel, by the way. So whatever the quantity is, let's say I in dB will be equal to 20 log I in whatever the scale that was, like watts per meter square, flux, whatever it is. So you put the value here and you are just doing a conversion over there. So these are interchangeably used. However, these you will fairly commonly you will see when the values are very low. For instance, intensities, they can range from they vary hugely. The last way to put it, or 10 or 12 orders, they vary depending on which field you are, which field of science you are in, right? Even in that field they vary considerably. That's the way to go for decibel, and this is the formula. Sometimes you will see also using 10 multiplied by log to the base 10, the same value I. So I in dB will be equal to this. This is usually, so this where we talk about power, we often use this because and when we talk about voltage, we often use this. Why is that? You can say this is the basic formula. However, power is V square by R. If R is a constant, then in order to express power, so this V square will come out, and there are all sort of things happening. But this is the typically thing that you will see. Does that answer your question?
Yes, we also does set reference in the term that is in denominator.
Yes, so here,
Usually.
yeah. So usually there is a, it's in physics, or in fact for any or for most of the sciences, I should say, you always measure from a reference. So for instance, when you're measuring the life of Earth, so you first define a time where you first define a point from which you start to measure. We call it the Big Bang. So from Big Bang, how many millions of years have passed, has passed on? Your life you measure in years. The day you were born was day zero, right? And now you measure life from that point, distance, everything. Here also there is a reference taken, so you can take it to be I reference, right? From some reference, how far away are you? So when you remember, you said 5 to 10 kilometers, right? You took maybe room as a reference and you measured distance to college, correct? Here I took reference as Earth and measured distance to the sun. Here I took, so there are two atoms here. I took this as the reference as origin and I measured this lattice constant A, which is 10 to the power minus 10 meters. Here also there will be some reference, right? So we usually put it in the denominator. Why denominator? Because if log A upon log A by B is log A minus log B. That's what you are doing here also, right? To get the absolute value, you just deduct the reference values. That's what we are doing here. So AD by AC, which you asked, right? AD by AC. Ideally, AC should be 0, right? And so if AC is 0, AD by AC will blow up to be infinity. And log of infinity is infinity, or that, or not defined, I forget. Whatever it is, it will be very huge number. Okay, but ideally AC, in real practical life, AC will never be 0. It will have some value. It may be minus 3, it may be minus 5, minus 10, minus 11, whatever it is, it will be some value. How? But the only thing that matters, if you remember that formula, it was something like AD V in plus minus V in minus plus AC and their averages. So if AD is greater than AC, right, you can neglect this term entirely. So that's why that's why we're interested only in the ratio, not on the absolute values. That's for it is to more important as far as the CMRR is concerned, right? Obviously we want a higher value of AD for higher gain. That remains independently true, right? I hope that answers your question, Pratik. Yeah.
Thank you.
Yeah. Any other questions for today's topics? If not, then I'll stay back to discuss doubts of let's say op amps in general, or Zener diodes, or diodes in general, or some digital electronics topics. If not, if you find some doubt, you can email me. I've shared the email address. Feel free. Okay.
Sir, can you explain Smith trigger in short? Just
Okay, I've forgotten Schmidt trigger. Just hold on a second. Let me pull out its circuit. Okay, just hold on a second. I know it. Schmidt trigger. Okay. Let me just open in a tab, and then we can share the tab and we can talk there. Schmidt trigger. I'm trying to search. Hold on.
So I would like to share a fact about that decibel thing.
Yeah, please go ahead. It's awesome when people. Yeah, go ahead. Hello.
The sound in logarithmic fashion. So a sound which actually 10 times power. So
Yes.
these bells and decibel, these units actually translates the output signal what according to the what human ear hears.
Oh, okay. So you're saying decibel is essentially you said the 10 times difference. So but 10 is I mean humans cannot decipher it's exactly 10 times, right? We can say it's louder. That much I can agree on, right? But you cannot say it's 10 times. So the factor of 10 is more of a, how should I put it, is an analytical frame of mind, not a, like a brain
Yes,
cannot
yes.
comprehend it's 10 times. If I
Yes,
tell it
yes.
it's 10 times, it can believe it or not believe it, but it cannot calculate. That's what I mean. It can say it's higher or lower. Yeah.
Yes, yes. Actually, I studied it in our laboratory manual,
Okay.
where we are converting the system output in phase shift in network or something.
Uh-huh.
It was written that like the bells and decibel systems are based on what human ear can comprehend. So
Okay, that's very nice to hear such things. Sometimes it's how things evolved in science. All right, I think I'm not able to find a proper consolidated diagram in which it has waveforms as well as the typical. I Yeah, I think this will help. Okay, now. Can you see the screen? This is a search result from YouTube, Google Images.
Yes, sir.
Right. So you can see. I hope you can. Is my cursor also visible? The mouse cursor. Or
Yes.
okay. So you can see this is assuming it's an ideal diode. So it's a positive feedback. You can see the output node is talking to the positive, the non-inverting terminal, and we're applying an input to the inverting terminal over here. And naturally, this is the VD that we have applied. And so as we talked about in the comparator, it's an unstable circuit. So it will always be it will quickly saturate. Okay. So what it will do is that essentially you have to write some expressions. What it will do is that, so let's say it says it is V in is at some low voltage, V in is some very low quantity. Okay. So what's going to happen is that since negative terminal is at a lower potential as compared to some positive terminal, right? So this will continue to be in comparator says the positive value is higher than the negative value, so it will signal a high output, which you can see over here just beyond this left this beyond this vertical line. Sorry, you can see that. So this is the region that we are talking about. Okay, now what will happen if that if V in crosses a certain threshold, if you are entering this region. Okay, if you are entering this region, but so you can clearly see then the V out has gone negative. Why it has gone negative? Because your negative terminal does now have a higher voltage as compared to the positive terminal, and when you compare them, the output simply says okay, go low. So output will go low and it will look something like this. Again, what will happen is that when the other threshold comes, so there are two terms here, UT and LT. I'm forgetting what to stand for, but essentially the idea is that it triggers only at certain points, right? So it triggers as 1, 2, and 3 for in this case, and that's how you
So
get.
it is like upper threshold and lower threshold, I guess.
Okay, correct. Yeah, that makes sense. Upper and lower. Correct. So what's going to happen is that so it gets it's not like every time it hits it gets triggered. It has to compare these two values, and this value will depend on R1 and R2. So please note that this is not the R1 R2 don't have a role. So whatever the value of V out, right? V out will be always saturation, like plus 15 or minus 15. But how much of it is being fed into this terminal? It will be a ratio of R2 by R1. So it because it's a potential divider essentially. So that's what it's going to happen. So it's going to be determined by these values, and it will only get triggered twice in a cycle. So that's why you see this hysteresis kind of loop. You have to go through. I mean, I'm not brushed up on this, but the idea is that triggering happens only due to the comparison. So that was the core point I was trying to highlight in that slide that I showed. So it's the triggering part. You have to maybe write down a few expressions. Okay, and if you still feel a problem, just drop an email to me. I'm more than happy to discuss it. Okay.
So then if we just go back to the problem where the answer wasn't matching, the circuit is similar and the output which was given in the answer key, it's also looking like
Okay, so yes.
the
So you are arguing that that was a Schmidt trigger circuit. I guess that's what you are coming to next, right? If now that you say it is a Schmidt trigger circuit, correct? So then there is something else happening. Okay, what I'll do in the next class, I'll discuss this problem again. Okay,
Okay, sir.
I'll do this problem again, and let's try to figure out what did I miss. Fine. Let's do this again next class.
Sure, sir.
Thank you for pointing it out, by the way.
Hello, sir.
Hello. Okay, just
Sir,
just a minute, Harish.
I have doubt about STR.
I know. Let's just finish. But so, any other doubts regarding op amps or digital electronics or anything?
Sir, can we say in Smith trigger that if we have feedback circuit
Mhm.
and if we change the polarity, that then it will become Smith trigger.
Polarity of what?
Polarity of voltage, input voltage.
No, that's what I was saying. It's not necessarily true. It has to depend on the. There are some other factors also. What kind of feedback do you have? What kind of saturation voltage do you have? What kind of input voltage are you providing? So there are. It's not. I mean, it is happening that it's the trigger is itself based on the input voltage. You're correct to that extent, but there are some other factors also which are playing a role. It is an oscillator. If you mean to say it's an oscillator, then yes, that is correct because it's positive feedback. But there are some other factors which are playing a role here. So we need to, I mean, be wary of that also. Okay.
Okay.
Yeah. Yes, Shiv Narayan. So what's going to, I'll share my, first is my email ID in case you have doubts or anything. Second is the YouTube link for my channel where I upload all the sessions that I have conducted till date, which would be around 20. So out of those 20, 14 are on electronics part and 6 are on special theory of relativity. So you are welcome to go through them. If you find any concerns or some problem I did wrong, some concept I missed, or you're welcome to point it out. Write me or comment or whatever you find fair. That's it. All right. Any other doubts on electronics and stuff? If no, then I'll take up the doubt on STR. And remember, no sessions for next 2 weeks. The next time we'll meet will be on in the next month, February 1st, 6 to 8 p.m. Okay. Thank you for your patience, everyone. If you have no doubts, then Harish, please go ahead.